we're skipping a generation.
Something ain't bad.
Something's wrong. Good thing you're in this class. Okay. We're going to go over number 4. This has 4 parts for number 4. Everyone had a chance to read it. The first part is asking you to fill in the table. All right? So if we look at this function, this is the original function f. And if you notice in the first row of the table, they did these different intervals, and they're all positive. Because what do you notice about all of the y values for this function? They're all above the x-axis. So all the y values are positive. Everyone okay with that? So they fill that in for you. That's nice. Now, to fill in the next row, all right, this would be the sign of the first derivative. You can do this a couple of ways. All right? You could if you wanted to. Right? I would not recommend this way, but you could just start taking tangent lines. Right? So if I did a tangent line right there, what is the slope that I just drew with that green pen? Positive, right? So that's going to be positive. Or what most students will do is they'll look at how would you describe this function as you're moving from -5 to -2? It's increasing. So if your original function is increasing, then the sign of your first derivative better be positive. Okay, now what's happening from -2 to 0? Decreasing. So if our original function is decreasing, then the sign of the first derivative should be negative. Okay, what's happening between 0 and 3? We're increasing again, so positive. And then finally, yes, you're back. We are decreasing from 3 to 5, so negative. Good timing. We only just started number 4, so I think you can catch up with us. Everyone okay with that second row? Okay. Now, if you look at the third row says the second derivative. Now, when I think of the second derivative, I usually go straight to concavity. All right, so concave up, concave down. Remember, concave up, you're thinking a cup. If you poured water, it would hold the water like a cup. All right, concave down is like a frown. All right, if you poured water, it would go down the side. All right, so look at -5 to -2. If I were to pour water at the top of this parabola piece, what would happen to it? Would it hold it, or would it go down the side? So this is concave down. It's actually concave down all the way until x is 0. Right, you see this parabola? That whole thing is concave down. All right, so it's actually going to be negative for the first 2 openings for the second derivative. Now this one is a little tricky. That's why I put this on the review, all right? Because I don't think we've actually done this before. Take a look at the next 2 pieces. Do you see this piece here? And do you see this piece here? What would you say to describe those pieces in terms of what type of function they were? They're linear. Very good. They're lines. And we actually, just for fun, we could actually write the equation of this line pretty easily, right? What's the y-intercept? 5. And then what is my slope? Up to right 3. So my slope would be 2/3. Okay? So if I took the derivative of this, what would my derivative of 2/3 x plus 5 become? 2/3. All right? Now, if I took it again, which is what I'm asking you about, what's the derivative of 2/3? 0. So this is, I don't think you've seen this before, but if your original function, in this case, these pieces are both linear, they're lines, when you do the second derivative, you don't have a value. It is 0. So you're going to write 0 in those rows. And I don't think you've seen that before, but hopefully now, if you see this going forward, you'll be able to put zeros when it's applicable. Okay? Now, one thing you might notice, maybe this will help as well. Do you see how when I did the concave up, concave down, right, this part was like a curve? Well, how would you describe this? Does this look like curves? No, it looks like pieces of lines, right? So that might be also a dead giveaway. Something interesting is going on if it doesn't have that curve for the concavity. All right? Now, there's a tiny little space, because technically if you want full credit for this, you need to tell me why you put these things. So I'm going to write super small. You should too. Write super small. I'm going to explain kind of what we just said, but in some words. All right, so I wrote that f prime of x is positive between -5 and -2 and between 0 and 3 because f of x is increasing. So sorry, it's so small. F prime of x is positive between -5 and -2 and between 0 and 3 because f of x is increasing. All right, I'm going to do the same thing, but for the other two, right? -2 to 0 and 3 to 5, but I'm going to write that it's negative because f of x was decreasing. So that takes care of the first row, or at least I should say the first row that we filled in, which was actually the second row that we care about. All right, so for the last row that we filled in, all right, I'm going to say that f double prime of x is negative between -5 and 0 because f of x is concave down, right? Remember, like a frown? So f double prime of x is negative between -5 and 0 because f of x is concave down. I know you probably don't have much room, so I'm sorry. I'm running out too. Try to squeeze this last little bit in. Right? I'm going to say f double prime of x is 0 between 0 and 5 because f of x is linear, right? Those pieces were lines. So f double prime of x is 0. All right, I'll let you guys finish filling that in. When you do this next week, right, make sure you write these sentences. Okay, make sure you write these sentences when I ask you to do this next week. If you just do the table, it's not going to give you full credit. Okay, so make sure you do the sentences as well. Everybody good on A? Let's go to B. So B says there is no value for x in the open interval -1 to 3 at which f prime of x is equal to, that would be the slope of the secant line. Explain why this does not violate the mean value theorem. So let's just real quick state that the mean value theorem would say that between -1 and 3, there would be a value x that when you evaluated it in the derivative, it would be the same value, right, as the slope of the secant line. So that's the line that connects the endpoints. Remember one of the questions we looked at yesterday in our multiple choice review went over this, okay? Now that is true only if your function is continuous and differentiable. So let's take a look at our function. Remember, I just look at -1, just look at -1 to +3. So -1 to +3. Is it continuous? It is. I don't see any like jump discontinuity or removable, no discontinuity. Is it differentiable? Where is it not differentiable if you're saying no? What at x value? What x value? At 0, right? If this value x is 0, how would you describe what's happening when x is 0? What? Sharp what? Not sharp object. Sharp turn or sharp corner. Either one is fine. Sharp turn or sharp corner means, am I able to take the derivative at x equals 0? No. So what you're going to write is, right, the reason this doesn't violate it is because the function is not differentiable at x equals 0. So the mean value theorem Yay, more students. Doesn't apply. We're on number 4. Do you guys have a pass from someone? Perfect. Thanks. Everyone okay with part B? Okay. Part C. Find all values of x in the entire interval, so -5 to 5, at which the graph of g has an inflection point. Now, we haven't mentioned this yet, but in the problem, the beginning of the problem, it said that g prime of x is the same as f of x. So I actually, for the next 2 questions, I'm just going to cross out, see where it says f? Right, so we're going to cross out where it says f. I'm going to rewrite that to be what? No, I'm going to write it to be g prime of x, right? So this is the derivative graph of g, okay? So to figure out where the original function g has points of inflection, I'm thinking where the second derivative would change signs, right? Second derivative going from positive to negative or from negative to positive. I'm trying to teach you guys that if you're at the second derivative stage where you're looking at where the sign is changing, that means the one above it, so the first derivative, would be changing from increasing to decreasing or decreasing to increasing. So in this function that's graphed, where is it changing? What x values? Is it changing from increasing to decreasing and decreasing to increasing? What you got? I heard 0, yes. -2, I think. And which one? 3 does count, yes, because it is changing. Very good. It's changing from, in this case, increasing to decreasing. So I'm going to write down those 3 answers. X equals -2, x equals 0, and x equals 3, because the g prime of x function is changing from increasing to decreasing or decreasing to increasing at those x values. Okay, one more question, and we'll stop the recording. One more. At what value of x does g attain an absolute maximum on the closed interval -5 to 5? And give a reason. So remember this function that they graph for us. I'm now thinking it's the derivative of g. Okay? So the g prime function is here. And we said earlier, what do you notice about all these y values, all the y values of this graph? They're all positive, right? They're all above the x-axis. So if the sign of g prime of x is positive for this entire time, what does that tell me is happening over -5 to 5 for my original g of x function? It's increasing the whole time. So guys, if I start at -5 and I'm just going up the whole time, when am I going to hit my maximum? If I'm here at -5, I'm going up the whole time. And here's 5. At when? At 5, at the very last point. That will be your maximum. So the answer for part D, oops, my bad, right here is the absolute maximum will occur at 5 because g of x is increasing over the interval -5 to 5. All right, and I know this because the y values for the derivative of g prime of x, are all positive.